We've been looking at how to write the electron configuration of the various elements. And at this point, we've already labeled our periodic table so that we have an idea of how the electron configuration of an element might end. Right? So just to review, the rows have been labeled from 1 to 7. And the columns have been labeled. The metals, for instance, are column S1 and column S2. And the columns on the right have been labeled from P1 to P6. So let's take a look at how this might help us to very quickly be able to figure out the configuration of a particular element. Let's try barium. The first step is to find the number of electrons in the ground state and the ending based on the row and the column. So first let's locate barium. Here it is. Barium is down here. And it is located in the 6th row in column S2. So we know that barium is in the 6th row and in column S2. And so we know that the ending is going to be 6s2. We also know that the number of electrons has to be equal to 56. 56 protons in the ground state, 56 electrons in the ground state. So let's locate that 6s2 in the filling order. And there it is. And so we'll just write the ending. Give yourself some room. 6s2. That's the ending of barium. And then write the preceding orbitals as completely full. Let's work backwards. 5p filled at 6, 5p6. 4d filled at 10. 5s filled at 2. 4p filled at 6. 3d filled at 10. 4s filled at 2. 3p filled at 6. 3s filled at 2. 2p filled at 6. 2s filled at 2. And finally 1s filled at 2. This is the electron configuration of barium that has 56 electrons. Now, this third step is to check to be sure that the number of electrons is correct. So let's add up all these superscripts. Specifically, 2 plus 2 plus 6, that's 10. Plus 2 plus 6 plus 2, that's 20. Plus another 10, that's 30. Plus another 10, that's 40. Plus 6, 46. Plus 2, 48. Plus 6, 54. And 2 equals to 56. And so therefore our answer is probably correct. And it is. So there it is. This is the complete electron configuration of barium. So let's try another element now. This time, let's try selenium, a nonmetal. Let's locate that on the periodic table. Find out how many electrons it'll have in the ground state. And also, let's use the periodic table to find the ending. Here's our periodic table. Let's see. Selenium is right over here. And so we know that it's in the P4 column, and we know that it's in the 4th row. So the ending will be 4P4. Let's write that down. What else do we know just by looking at the periodic table? We can see that selenium has an atomic number of 34. Therefore, in the ground state, selenium will also have 34 electrons. Let's use the filling order and work backwards like we did in the previous example. And there's 4p right here. And so let's write that down. 4p, specifically 4p4, because that's the ending for selenium, and then work backwards. 3d will be filled at 10. 4s will be filled at 2. 3p will be filled at 6. 3s will be filled at 2. 2p will be filled at 6. 2s will be filled at 2. And 1s will be filled at 2. So this is the likely configuration of selenium. Let's see if these superscripts add up to 34. Let's add these up. 2 plus 2 plus 6, that's 10. Plus 2 plus 6 plus 2, that's another 10. These 10 right here add up to 30, plus another 4, that is 34. And so there you go. This is the correct electron configuration of selenium. All right. Now there's a warning over here. We have to be very careful with the energy level of the d orbitals. Remember, the energy orbital are these first numbers right in front of each of the sublevels or orbitals, right? You have to notice that after 4s comes the orbital called 3d. And so that's one energy level lower than 4. And so the way to use this technique is to be careful and remember that the energy level for d orbitals is one less than the row number. After 4s is 3d, after 5s is 4d. This is all completely theoretical until we try it on an example. So one of the better examples to try first is nickel. So let's give that a shot with nickel. Let me get rid of these marks. Let's find nickel on the periodic table. And here it is. Nickel is number 28. And so we have to try to figure out what will be its ending. We know it will have to account for 28 electrons. So let's take a look. We have these D columns labeled. And if we continue with the numbering, we can see that this is going to be D8 for nickel. But since it's in the 4th row, we might be tempted to say that it's 4D8. But no, remember, the energy level for d orbitals is one less than the row number. So don't write 4d8. The ending for the electron configuration of nickel is 3d8. So let's write that down. Nickel will be 3d8 based on the row and column. Remember, the row, even though it's the 4th row, because it's D, you have to put one less as the energy level. So it's 3d8. And the number of electrons is 28 for nickel. So let's do that, same way that we did it. Now that we know that the ending is going to be 3d8. So just begin at 3d8. And then work backwards with completely full preceding orbitals. 4s will have 2. 3p will have 6. 3s will have 2. 2p will have 6. 2s will have 2. And 1s will also have 2. Now let's make sure that all of these superscripts, which refer to electrons, add up to 28, which is what we expect for nickel. Let's see. 2 plus 2 plus 6 is 10, plus 2 plus 6 plus 2 is now 20, plus 8 does equal the 28. And so this is the correct electron configuration for nickel. Just remember, when you're dealing with a transition metal whose ending is in the d columns, the energy level for d orbitals is 1 less than the row number. Let's try molybdenum. Molybdenum is all the way over here. And looking at the row number, molybdenum is in the 5th row. But we have to remind ourselves the row number for d orbitals, technically the energy level, is 1 less than the row. And so molybdenum's electron configuration will end in 4 for its energy level. Even if it's in the 5th row, it's 1 less. So it's 4, and it'll be D4. It's in the D4 column right here. And it has 42 electrons. So let's make sure we write that. Molybdenum, we have to account for 42 electrons, and it is in 4d4. That will be the ending of its electron configuration, and there it is. So let's write down the ending and then work backwards. 4d4, working backwards, 5s2, 4p6, 3d is filled at 10, 4s is filled at 2, 3p is filled at 6, 3s is filled at 2, 2p is filled at 6, 2s is filled at 2, and 1s is filled at 2. Let's check. These superscripts should add up to 42. 2 plus 2 plus 6 is 10. Plus 2 plus 6 plus 2 is now 20. Plus another 10, that's 30. 36, 38, plus 4, 42. This is the correct electron configuration. At least that's what we will expect for molybdenum. All right? Now let's move forward to try to see if we can understand how we can use the noble gases in column P6 as a convenient point for the abbreviation known as the noble gas notation. Let's use the same principles that we applied earlier to write the complete electron configuration of neon, for example. So let's find neon. This should be fairly quick. Neon's right here. We have to account for 10, and it's going to be in 2p6. And so we're just going to end it at 2p6. and before 2p is 2s, 2p, 2s2, and then before that is 1s2. So the complete electron configuration of neon is 1s2, 2s2, 2p6. And you have to notice something here. The s and the p orbitals are completely filled. Completely. Let's take a look at argon. With 18, it will end in 3p6, because here it is, it's in the third row in the p6 column. Let's see. So it will end at 3p6. Let's move backward. 3s2, then 2p6, 2s2, and then 1s2. And that is the electron configuration of argon. And what should you also notice? You'll also notice that the s and the p orbitals are completely filled in the electron configuration of argon. Now on this page, let's take a look at krypton. Krypton is on the fourth row, right? Here it is, and in the p6 column. So let's see if we can figure out the electron configuration of krypton. Krypton will end in 4p6. And what comes before 4p in the filling order? It's 3d10. Before that is 4s2, 3p6, 3s2, 2p6, 2s2, and then 1s2. And if you add all of these up, 2 plus 2 plus 6, plus 2 plus 6 plus 2, plus 10 plus 6, that does add up to 36. And what else do we notice? We notice that in krypton, a noble gas in column P6, all of the orbitals are filled. And why is this a convenient spot to begin? Take a look at this. I'd like you to see, I'm going to use a technology trick here. Hopefully I'll be successful. I'm just going to duplicate this. I want you to notice that this portion, right? This portion, I'm going to change the color so that there we go. This is the electron configuration of argon, right? I hope you can see that that's the same thing as the beginning of the electron configuration of krypton. Essentially, using completely filled orbitals will help us to write the noble gas notation. Again, it's only theoretical until we use an example. So let's take a look. To write the noble gas notation, use the noble gas on the previous lower row, and then take note of the ending of that noble gas. Let's try this for calcium. All right? Let's find calcium on this periodic table. Calcium is right here. And we know it's going to end in 4s2. So let's make a note of that. Calcium will end in 4s2. Calcium ends in 4s2. Now, it says, take note of the ending of the noble gas on the previous lower row. So for calcium, calcium is right here. The noble gas on the previous row is argon, whose ending is 3p6. 3p6. It's argon 3p6. That accounts for the first 18 electrons. And so if we write 3p6, this will be up to here, up to this point, all of this filled up is the argon configuration. And then we simply have to tack on 4s2, right? So, essentially, the noble gas notation is written this way. Argon, that accounts for the first 18 electrons, this right here, with 4s2 tacked onto it. This is the noble gas notation for calcium. And how will we check? How will we check that this is correct? Take a look at the numbers. See this number that we wrote above argon? The argon configuration accounts for the first 18 electrons plus 2. Does that add up to the number of electrons we expect for calcium? Sure it does. It's 20. I just want to make sure that you understand that. So let me write the complete electron configuration of argon and for calcium. Let me show you argon first. Essentially, it's 1s2, 2s2, 2p6. We just wrote it a few minutes ago. 3s2, 3p6. And if you followed the same to write the complete electron configuration of calcium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now hopefully you began to notice that this portion of calcium, the beginning portion of calcium, is exactly the same as the configuration for argon. And so if we substitute this portion with this symbol of argon 18, all we need to do is add 4s2. And there it is, the noble gas notation for calcium. All right, that was just one example. Let's try another one. Let's try iodine this time. Remember, to use the noble gas notation, we need to take a look at the noble gas on the previous lower row. So let's find iodine first of all. Iodine's right here. And the noble gas on the row before iodine. Remember, the noble gas on the row before iodine is krypton. And so the noble gas notation has to be built on krypton that ends in 4p6. So the ending for that noble gas will be 4p6. So it'll be over here. And what about the ending for iodine? The ending for iodine will be 5p5, which is right over here. So therefore, this portion, if you fill in all the orbitals, that will refer to krypton. And then all you need to do is add the rest of this, filled of course, plus the ending, to understand the noble gas notation. So krypton accounts for the first 36, 5s, 2, 4d, 10, 5p, 5. And is that correct? Let's check it out. Iodine should have 53 electrons. And so let's add this all up. The first 36 are in a krypton configuration, plus 2, 38, plus 10, 48, plus 5, 53. And so here is the noble gas notation of the electron configuration of iodine. Now, go ahead and try some of the examples in the worksheet and refer back to this video if you have any questions.